m'entend? On m'entend, voilà. Ouais, c'est mieux. Okay. So the proposition is, we have the hypothesis, which is, you have eta, which goes from this sequence of blow-ups. So you have a m minus 1, eta 1. Here you have a Mori fiber space. In our case, just Fn to P1 or P2 to a point. And you have a E there, minus 1 curve. And then the conclusion, then you have the commutative diagram, Y, to Z, blow up of a point. The image is E. And then you have a sequence of blow-ups again. To something, which is W. Here, X, eta, product of Sarkisov link and automorphism. Okay, so that's what we wanted to prove. So we have done the case where the image was a point, so it's not a point, it's a curve. It's a curve. And then we have written Ex as a, it's in, yeah, X is Fn. We have shown that if it was P2, you could blow up something. And then we have Ex is ds plus df, where d is at least 1. And we have that s times ex is at least 0, which is, this is minus and d plus b. That's what we have, because if it was negative, we had that it was a negative curve, and then we showed that in that case we were finished. Okay, and now we have also that E is the pullback of AX minus some AI EI, where the EI was the exceptional, the pullback of the exceptional divisor on each step, and 1. Okay, so that's what we have yesterday. Now we'll calculate this. So we know that it's a minus 1 curve. So minus 1 is equal to E square. So you calculate that. So it will be this to the square. So EX square. Take the pullback, the intersection is the same. Minus sum of the AI square. And also you have adjunction formula. E times E plus K, ky, is equal to minus 2, because it's isomorphic. P1 otherwise would be minus 2 plus 2 times the genus, so but for P1 minus 2. So then it implies that so what I will find is that yeah, ky, we calculated that when you do a blow up, it's the pullback. At each step you gain 1. So it's pullback of kx. Sum of the EI. This you prove by induction, and that's why my basis was nice. Everything is no coefficient, nothing. Okay, and now what you can calculate? So you have minus 1, which is E times ky. So I multiply this by the other one. So this time this, it will be Ex times Kx. And then you have the sum of the EI times the EI, it's made -1. Then you have the minus, so it's made plus. So it's plus. So we know now what is the sum of the AI, and we know what is the sum of the AI square. So I will use this. So it's just some calculations. And okay, then Ex square, I say we know if we know what happens downstairs, but we can use it from the formula there. X square ds plus bf square. So it's d square minus n, so minus n d square. So this to the square, this square is 0, and then you have the products to 2 times d times b, because f times s is f times f square equal to minus n, recall s times f is 1, f square equal to 0. Okay, so we'll do some calculation. I hope that some of you follow this, and if there is a mistake, tell me. Okay, then minus k minus ky, we know what it is. Kx, sorry, times ax. This is what we calculated. So it was 2s plus 2 plus n times f. This is minus kx. Because you are in fn, we calculated 2 days ago, times ds plus bf. Okay, and now so you develop, so you have 2d times a square, so minus 2dn. You have 2 plus n for the square, the f square, it goes out. And then you have the s times f. You have 2 times b. And then you have the 2 plus n times d. Okay. So now I will write, I will make a, just to simplify a bit the notation, I will write epsilon. I call it epsilon, it's 2b minus dn. Okay, and then it's so this is equal, when I do this, I have a d times 2b minus dn, so d times epsilon. And here, in that case, I have 2d there, plus what remains as a 2d plus nd minus 2nd, so it's plus nd, minus nd, so minus nd plus 2b. So it should be 2d plus epsilon. Thank you. That's what I wanted to write, but because it's on my notes, but on the blackboard it's harder to do calculations. Okay, then now we have these 2 formulas. So we know everything. So I will use this formula. Okay, so just simple formulas. Then we will have sum of the AI. Epsilon. So if I take it from here, it's minus 1 plus minus 1 minus ex times kx, and so it is epsilon to d minus 1. We have epsilon plus 2d, and then here minus 1. Okay, and sum of the AI square, it's you can take it from the other formula, the top, it's minus 1, it's ax squared plus 1. And so it is equal to 1. Okay with this? Some are okay. Good. Okay, what I know, yes, I forgot to say, we have done the case where the multiplicity are large, so now they are small. So what we know is that 2ai is smaller than d for each ai. Okay, so I will use this so that I know that 0 is smaller than sum the ai d minus ai, because d is bigger than equal to. This is non-negative, and so it is d times sum of the ai minus 2 sum of the ai square. So 0 is smaller than this, so it's d times the first one. And then minus 2 times the second one. Okay. Okay, then I have, if I develop, I have 2d square, just 2d square alone, d epsilon minus 2 d epsilon, so it's minus d epsilon. I have minus d minus 2. Okay, so what you find, so this is smaller than this, so it means that d by 2d minus epsilon, which is 2d square minus d epsilon, sorry for the long calculation, is bigger or equal than 2d plus 2. So this is exactly this. I put the d minus 2 there. I have this. And of course, this is bigger than 0. Because in fact, it's bigger, it's at least 3. So, okay, then I know that, I already know that d is bigger than 1. So this one, so 2d. I have this. Okay, now I have 2d minus epsilon. 2d is bigger than epsilon, then because of this. And then, but epsilon, I recall what it was. 2b minus dn. Okay, and then we remember that because b is at least nd. So this is bigger than, if I can replace a b by nd, and then I kill, so it will be b is nd. Okay, so 2d is bigger than nd. So all these things to tell you that 2 is bigger than n. Because d is positive. Okay? Good. Why is it interesting? Because you are on Fn, so it's not F2, it's not F3, it's F1 or F0. Okay? So n is in 0 or 1. We have just two cases to do. If n is equal to 0, you have P1 cross P1, you will exchange the two, make a link of type 4. if s is equal to 1, you will contract to P2. And in both cases, you will see that you can apply the induction, and it will be better next time. Okay? So n equals 0. Then we will exchange we do a link of type 4, the link of type 4, because for me there's only one, I exchange the two vibrations. So what you have to think is that if you do this, I am there, I'm looking for whatever happens at the right. I will just do a first link and then apply the induction. So the first one will be just an isomorphism. And it doesn't change my morphism, but it will change my EX. So EX equal to DS plus NF is replaced by just exchange B. Sorry. B. You exchange the D and B. B S plus D. Okay. So what we just have to prove is that B is smaller than D. Okay. Okay, but then this is in that case we just replace here n equal to 0, and this is done. We just take this 2D. 2D is bigger than epsilon. Epsilon is 2b minus dn, but in that case, n equal to 0, so it's just 2b. So you have 2d bigger, strictly bigger than d, so good. Good. So when n equal to, so we have done just this calculation to find these two inequalities, and now we apply them. So for n equal to 0, I exchange the two vibrations. I can apply induction because I have decreased the d. Now the next step is n equal to 1. It's a little more work. So now you have your morphism to F1. In fact, you will contract to P2, make an isomorphism, and then blow up the point. Because in my notation, so this type type 3, I contract, and so I will do the inverse, which is type 1, and here I will just change the point. So you will go to P1, contract on a point, take another point, and blow it up. Okay? And I will have a morphism there because I will blow up a point that is in fact somewhere there. And so I will just change I will calculate here the formula there and check that the degree is smaller. Okay, so this inequality, which is what we need, will help us. So we have 2D. We have 2D bigger than epsilon. Epsilon, I recall that it's 2b minus dn. But then now n is equal to 1. Yes, so it's 2b minus d. So I put the d at the left, and so I have 3d bigger than 2b. Okay. This will exactly be the things to show that when you blow up, you decrease the thing. Okay. Then I will erase. Okay, then I have contracted, I go try to P2, and I will blow up a point. I will take another point. In fact, you have the point, some point which come from the blow up, the contraction to a point, but I will take one of the AI. Okay? So I'll take, of course, the maximal one. And you want that the multiplicity is as large as possible. So suppose there exists AI. In fact, if you can do the calculation, I will do it after, but I already tell you the result. Such that AI, what we need when you do this, AI is bigger than B minus D. Then that will be you want the AI to be big enough. In fact, it's exactly this. Then again, up to changing the order. A1 is bigger than B minus D. So I am in F1. My first blow up is just multiplicity 1, and then I will just contract. So I will do this here. I have eta 1, eta 2, and then y on the top. So I blow up a point, and now this point, I will check that it's not on the exceptional divisor, because the intersection with the exceptional divisor is smaller than is. What is my curve? Yeah, it's here. Ex is ds plus bf. S times ex is minus 1 now. So minus d plus b, so it's b minus d. Okay? So if you have a point which is multiplicity bigger, it cannot be on the exceptional curve, because on my intersection of my curve with the exceptional curve is bigger than this multiplicity. So it's outside. So you have a point, it's contracting a point. You have the point which is outside. So from here to here, I blow up 2 points, and then it corresponds exactly to this, and then another one. So you have a morphism there. Irrational morphism. Just from P2, I blow up 2 points, and here I blow up 2 other points. The same 2 points, but in the other direction. First, the other order. So now I will calculate the F1. So the new D is the intersection with the fiber now, but the fiber corresponds to a line downstairs. So downstairs you have 2 points. From here to here you have another point, so 2 points in P2. So you blow up the point. Now the intersection with the curve was B minus D, so you have multiplicity B minus D here. And here you have A1. So the multiplicity is bigger, so when you blow up, the intersection with the fiber will be, the degree minus the multiplicity will be smaller. the image of P1 and get D smaller as the multiplicity at the new point is bigger. Now you have to think that the degree D, it corresponds exactly to the intersection with the fiber, and so it's a line, in fact, in P2. It's the same intersection, but you remove the multiplicity at the point when you have done the blow-up. So you just make a pullback. So it's C tile this pullback of C minus the exceptional, so you have minus this. So if this is bigger, you decrease. Okay, then we are happy if this has happened. And now the bad case that we will show it doesn't exist. AI is smaller than B minus D for all I. We derive a contradiction. Okay, so we'll show that this is not possible, so we are finished. Okay, so I do the same trick as before. Some of the AI. I want to show that, so I take AI. If this is smaller, then I have minus B D. By assumption, this is smaller than 0. I have a sum, so everything is smaller than 0. Okay, and then it's sum of the AI square minus sum of the AI B minus D. And yes, the sum of the AI, you replace what it means. Here are also, and then you do. I think I will not do the calculation. Not so enlightening. It's just a simple thing. You replace and you get easy exercise. Okay, but then so you just replace some of the square, but by how much it was. Some of the AI, you replace everything, and then you get this. Okay, but then we knew that this is bigger than 0. This is bigger or equal than 0. This is, of course, bigger than 0, so there is a contradiction. Okay? We are done with this position. Until when is it? Okay, good. Then I will have time to prove the corollaries of this, which are the main interesting thing. In fact, you have a technical proposition. Call it a lemma, but it was important for me. I just call it proposition, and I will apply it to prove the theorem of Noether-Castelnuovo, proving the first the Castelnuovo, and then we'll prove also that every rational smooth surface is covered by A2, that we can contract -1 curve, etc. So I do all this thing now. It was a long calculations, and now we deserve to have easy corollaries. So if you didn't follow, just assume this, and now it will be easy to deduce everything. He did some calculation, he found something. And now you can just apply it. So I will prove first the result of Castelnuovo-Iskowski. So prove that every rational map between Mori fiber space is a product of Sarkisov links, what people call now Sarkisov program. fact, Sarkisov, he did not that at all. And he stopped maths, and when he came back after some years, he said, no, but why do you use my name for doing this? He doesn't want us to do this. Too late. Yeah, it's called always Sarkisov program. But I think it's a nice program, so I think it's not a shame to have your name after that. Program after your name. So it's really useful. In general, in dimension 3, you will see it next week. And more, dimension more also. So in dimension 2, it was already done 100 years ago, but we just translate it in modern language. Okay. So theorem. So the version I write, it's from Skowski 1995, but before, I mean, it's basically the idea of Castelnuovo. So you have the rational map. These are Maury fiber space. So in dimension 2, now we are just with Fn to P1 or P2 to a point. And now you have a rational map which has nothing to do with the B1, B2. Then phi decompose into Sarkisov link and automorphism of Maury fibers. Okay. So now the proof will be easy now with the position. So you write, you have x1. In fact, I need some place at the left. So if you take notes, some place there. Okay, you start by your phi. It's a sequence. You blow up the base points. So you have your eta 1, eta 2, eta m. You have the y. Don't care what is at the right. You have the base points there. And now I will do the induction on m. Okay, so now if m is equal to 0, if m equal to 0, what happens? Then it means that you have blown up nothing, so phi is not in fact a rational morphism. So you have two possibilities. It's an isomorphism, but then it's an automorphism, in fact, because I have for each isomorphism class I have only one guy, so it's auto. So, and then we are done. Or it's not an isomorphism, so it's a blow up of something, a sequence of blow ups. Okay, but then what you have to contract something on your variety. Okay, so contracts some negative curves, at least one minus one curve, at least one minus one curve. When you have a blow up, a sequence of blow ups. When you do one blow up, you have minus one curve. When you do another one, then the minus one can become minus 2, minus 3. But then you have always one minus one curve and some other which could be contracted, which are negative, more negative. Okay, but recall that x1 is P2 or x1 is Fn. So here it's not possible. You have no negative curve. So in Fn, we show that you have only one negative curve, so n at least one, and it has to be the section. So because there are only one, you find that, in fact, n equal to 1. And then here you have only one negative curve, it's -1 curve. Because on the other one, you have only one negative curve, but there is no -1 curve. So in fact, it's F1 to P2. So it's just my type 4 plus an isomorphism. Type 3, sorry. Type 3 followed by auto of P2. Okay, so that's if m equal to 0, I'm happy. So now, suppose m bigger than 1. So this was the case easy for m equal to 0. Now for m at least 1, you have to work, but no, we don't have to work. We have a proposition now. So we can you can use it. We take the last curve. We define E. It's eta m minus 1 of Pm, last exceptional curve. So you have a blow up of a point. The last point, it's a -1 curve. And now we will apply the proposition. Okay, and now, oh yes, I wanted to do it now. I said to have place, but in fact, I'll write it again. Okay, I have my proposition. I know I can contract the E. It's the blow up of something. So in fact, my tau is equal to eta m. It will be the z. I have two contractions of the same -1 curve. You can check in coordinates. It's the same. This is easy. And then you have the W. W, and then this is a sequence of circuits of link. And auto. Okay, that's what the lemma does. So now I just have to find by induction. I consider this map, and now this map has a decomposition which is smaller. Because it just I go down from Z. You have the morphism, and then now you apply induction. So you have a sequence of circuits of link. Now you come from here to here, and you have blown up one guy for nothing because it's sorry. I think I did a mistake. Sorry. No, I think it's false. I should take this guy. Well, otherwise the lemma is stupid. I have this guy. Epsilon 1. Epsilon R. Sorry. The mistake is epsilon R -1 of, I don't know, some Q. R, last exception. And now, sorry. I do the other way, so it's at the right, which makes more sense. X2, X1, X2, and then you have the first one. This will be my Z now, and now I have a birational morphism to W. This is a sequence of circuits of link. And now it's okay. Now you have a resolution now, which is smaller. And decompose X2 W into products of circuits of link and auto. Okay? So now we have proven the so with this theorem we have proved 2 days ago that this implies that it's a product of Jonquière and so every rational of P2 it's a product of Jonquière and linear, and then you have to work a bit on with the Jonquière to do that it's product of linear and quadratic. A simple exercise, but I will not do it now. I will do other corollaries. Corollary. A. Every smooth projective rational surface is a sequence of sequence of blobs is obtained from P2 or Fn and different from 1 by a sequence of blobs. Because if you have F1, you can see it from P2 by sequence of blobs. So every smooth projective rational surface is a blob of P2 or a surface, a sequence of blobs. You have S, it's rational, so you have rational to P2, and now you have your Y there, and so if it's an isomorphism, you if it's an isomorphism, it's okay, it's P2, but otherwise you have to blow up something, and then you do by induction. So I guess I do the other direction. Yeah, from here. Okay. So it's if eta it is a isomorphism, and it's okay. You have just P2 to S, which is a morphism. So it's P2, and otherwise you have otherwise take the last -1 curve, then you do the same trick as before. You compose, and then you reduce. Okay. Take the last E. Same contracted. I think on the right. Just check it, but I think it's on the right. And apply induction. Apply proposition and induction, like before. Right, so you kill the number of points you have to do. I think it's maybe on the left. At the left, sorry. It's okay, it's finished. It's the blow up of P2, and otherwise at the left, contracted. Okay. So you just you factorize, and exactly same proof as before. Okay, now you have the two this corollary, and now another corollary. So you have E in Y, smooth projective. E square is equal to -1, E isomorphic to P1, then it's a blow up. E exceptional device. So it's Castelnuovo criterion. For contractibility, you can contract a -1 curve. So here, now we prove it for smooth rational surfaces. then fashion. It's still true, but I didn't prove it. It's not a corollary. Okay, and then how do you prove this? But you apply corollary 1, corollary A. So Y is the blow up of FR Sabur, and then you apply proposition, and then it's finished. Oof. Oof. Corollary A plus proposition. So you see Y as a blow up of something. So you can see it like this. Like here. You can see it as blow up of something. And then you have the E, and then you have the toe. Finished. So that's just this. How much time? 10 minutes. Very good. I have time to erase my blackboard. Okay, and then we can also see that every smooth rational surface is covered by charts which are isomorphic to A2. This is also another corollary. So corollary B, C. C. So S smooth projective rational surface. There exists UI finite. In fact, I think 3 is enough, but you want to do the best way. Me, I just say finite. So that union of, so it's open covering. So everything is open, and the union gives everything, and UI is isomorphic to A2. Okay, so you can cover any smooth projective rational surfaces by some A2. Okay. So for P2, you have 3 charts, which are just 0, not 0, x1, not 0, x2, not 0. If I take coordinates x0, x1, x2, it's just... Okay, so that's classical. Fn, we have the 4 charts we have seen days ago. x0, not 0. We'll say xi, not 0, and yj, not 0. You have 2 possibilities for I, 2 possibilities for J. You have 4 charts. I think you can, if you want, you could do a very strange chart and make it for 3. Okay, and now you assume that you have your S. Now it's by the corollary A. Apply corollary A. Then you have a rational morphism sequence of blow-ups. R, theta 1, and then X. This was in Maury fiber space, so it's Fn P2. Okay, and then you apply induction. So what just you have to check that when you do a blow-up, if it was of this form, it stays of this form. Okay. So for each, we don't need to show. So if O for S, then O for blow up of a point in S. Okay, but then you just take the P, if it's outside of UOI, okay, you take the preimage, it's okay. And if P, okay, take the preimage. And if P is in UI, which is isomorphic to A2, then I call it pi. Then pi minus 1 of UI is covered by 2 open subsets. We have seen it the first day. Subset isomorphic to A2. So for each chart, you take it back, you have twice more. So with my calculation, basically you have the number of base points, the thing of before, maybe times 2 to the power the thing. So it's really bad, but I don't care. It's just finitely many. I think there is an article, yeah, maybe some like 10 years ago, where they prove, I think, that you can do it with 3. And you cannot do it with 2. No, if they were covered by A2, they would be rational. Rational. Good question. I don't know who is we, but now here, I don't know, but maybe in 10 minutes I will think. And maybe it's easy, but maybe it's so hard. I don't know. I didn't. Probably yes. You have to take the minimal ones and check for each minimal ones what happens. But I mean, minimal, rational, there are not so many. Yeah, exactly. So you have to do all the 5, 6, and 8. Yeah. And yeah. Yes. So interesting. I don't know if it was been done or not. Good question. Okay, and the last thing, just as I said before, so we know already that beer P2 is generated by haute P2, which is PGL3, and the Jonquière. And so that was proven. And then now we can just check that it's beer P2 is automorphism of P2. And then this sigma. And the sigma, in fact, if you can see it there. Okay. The sigma, you have the 3 points. And then you blow up the 3 points. That's the classical version of doing it. There are many. You blow up the 3 points and then you contract the 3 lines. That's what you do. And then you get, okay, that's the sigma. But in fact, if you see it's in Jonquière, if you see it in Jonquière and you decompose in circuits of link, so you have P2, sigma, then you just go to F1, and now you have one of the points you have blown up, then it remains 2 points, so you choose one of the two, you do a circuit of link, because it's outside of the -1 curve, you go to F0, and now you have the second one, which has nothing to do with the rest, it's there, it's a general point which is there, and then it's F1. So that's this, okay? So that's what sigma does. And then in general, what you do, you have P2, you just have to show that a Jonquière is there, of course. So now you take a Jonquière. So because it's a Jonquière, you go to F1, then you will go to some Fn in the middle, so F2 or F0. And you don't know where you go, but at the end you go to F1. Okay. And then you try to decompose in products of sigma. So one way could be to argue in the induction on the number of base points. I think it's a bad idea. The first thing is to show that you can only have F1 and F0. Because at the beginning, if you have some Fn, at the right, at the left, you put a sigma quite general, which has nothing to do with the base point. You blow up two completely arbitrary base points. You do links there, and this will be a sigma. So up to automorphism, you apply automorphism. And then you will do 2 points general. Very general, you go to F0, F1. So it seems that you have done something much more. So this will be 2 general points. You take 2 general points, you do the link and the link. And this will be sigma up to automorphism. Okay, and now these 2 general points, you take it back there. And now you do the same. So then Q1, Q2, and then you do the same here. And again, this one will be product just sigma up to automorphism. And now if you have done this, you didn't increase the number of base points, but you make it that the Fn decrease. And after finitely many steps, you have only F0, F1, and you can continue, and then they are just all general, and it's finished. And then you just see that you see sigma, 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 sigma with product. I mean, it's a bit sketchy, but it's the idea. It's the proof I saw in, I think in algebraic Cremona, she proved it like this. But I think it's also the proof of Castelnuovo. So what I did with the numbers and so on, it's not what the people did before, but it's the same idea. You do circuits of links, you have integers, you find maximal multiplicity, just that I change basically the base and put a -1 curve, but it's the same idea as what is the classical proof of Noether-Castelnuovo, of the circuits of program, and it's exactly what Castelnuovo did, but a long time ago, but he stayed in P2, so it's a bit more complicated, but it's the same idea. Okay, thank you. Yes? I think there was an article that proved that it was 3 charts, but you have to, you see in my thing, I think you do like this way. Well, first you have to do this for Fn. You have to not take the standard one, but move something. In fact, each time you have a chart, you have a curve on the complement that you have removed, and there are some which are, in Fn you have 2 curves that you take, so you have many possibilities to put an A2 there, and then you put it in a good way so that the intersection of your, I think you do 2 charts, so that what remains is just finitely many points, and then it's good. Then you have a third one that covers this, and that's how you do for this, and then you can try to do it in the top. You know this proof? Or? Yes, but no. So it works for any smooth projective rational surface? You see it for Fn, okay. But then you have to do it for blow-ups, and then for blow-ups, I think you have to move a bit the chart so that the points are just on one chart, And then you have to do some clever things. I mean, it's not that easy, but I think it's 3 for any surface. Yeah, it's clear that you cannot do better than 2, but than 3, but yes, they proved that it was 3. I think it's an article. I don't remember. Some like 10 years ago. I can find it maybe for next week. Yes, so I asked the question at the beginning. So there were 2 questions. One like very positive and optimistic, which was in dimension 3 and more. Is every, so I can write it again. Question. Naive question, but it was good that I asked this also on matter flow. Nobody answered, so it's good that we are here with experts. The naive question is every smooth projective rational variety covered by of dimension n covered by an. So answer yes for n equal to 2 and no n equal to 3. And the reason it's Mihaly sent me the paper yesterday. Then you have, in fact, you take, for example, a Fano of Picard rank 1. Picard rank 1, so there is a family. There is a classification with 81 families. Most of them are not rational, but you take the ones which are rational. I think it's like 10, 15. I don't remember, but more on that number. And then among them, there are only 4. 4 which contains, which are covered by some AN. In fact, not covered, which contains. So there are some which do not contain any S3. Okay, so the answer is no. And then the conjecture, which is less naive, it's that covered by open subsets of AN. This is open. Open and at least 3. And the same kind of proof that I did. Okay, first you can show it for the minimal one, so you have the Picard, the Fano, and so on. You could probably prove that. I think it may be true, but we don't know. For the minimal ones, I think already that is not so clear. But then when you do blow-ups, you can see that it works. So if it works for something, you blow up something, a point, a curve, anything smooth, then it stays, it works. The problem is contraction. As was explained yesterday, you have the weak factorization. So you just need to prove that when you contract something, if upstairs it's uniformly rational, this is the question, then downstairs it is. And this is not so clear. Maybe true, maybe not. Okay.